Okay, so let us start today's session. This session will be live session 11, and this session will be on micro and nano scale manufacturing. So it is already crossed 5 p.m. I'm starting this session. You can always go through the video lectures which will be uploaded in YouTube. So in question one, it says to match the following. So there are three different kinds of welding techniques, which are one is arc welding, one is power beam welding, and the third one is solid state welding. So if we see in arc welding is basically a fusion welding. Of course, power beam welding is also a fusion welding. So in fusion micro welding of arc welding technique, there will be a regulated and controllable outputs which will be less than 1 ampere. So basically, regulated and controlled outputs of less than 1 ampere are obtained. Mainly, these are gas tungsten arc welding, plasma welding. These are mainly arc welding. So if you see here in arc welding, you have gas tungsten arc welding, also plasma arc welding, uh, mainly in this gas tungsten arc welding and plasma welding. Peak pulse controls the penetration background, and this penetration background pulse allows solidification without extinguishing the arc, right? So in this arc weldings, peak pulse controls the penetration and the background pulses, they allow solidification without extinguishing the arc. Okay. Now, if you see in power beam welding, what happens in power beam welding? Basically, there is a very fine control over power and positioning. So, if you see in power beam welding, uh, in power beam welding, fine control over power and positioning of the power beam. So, they are very much precise and accurate in nature. And in power beam welding, it focuses a high energy beam onto a very small spot size. So because it focuses a high energy beam, there can be deep penetration without minute amount of distortion. So there will be deep penetration with little or no distortion of the workpiece. So in power beam welding, it will be deep penetration with little distortion. And what happens in solid state welding? In solid state welding, no melting of material is involved, right? So in solid state welding, basically joints are made when plastic flow occurs at the interface. There will be intimate contact happens, and it forms a bond because of that intimate contact. So there can be three different types of solid state bonding, namely ultrasonic welding, friction stir welding, diffusion bonding. You have gone through those techniques in your contents of this week, right? So in solid state welding, basically there will be no melting of material, and uh, it can be basically a kind of atomic diffusion. So if you see in ultrasonic welding, there will be a sonotrode tip which will be vibrated over the workpiece at a very high frequency and low amplitude vibration, and because of their vibration there will be kind of shear deformation at the interface, and because of that shear deformation there will be kind of what should I say, there will be a joint made at the interface because of those shear deformation and diffusion at the solid state, right? And even in friction stir welding also, because of that tool rubbing over the workpiece and penetration of the tool pin, there will be kind of stirring of stirring of the workpiece material, and it basically tool forces the material to mix up together, and it will be a mechanical intermixing, and because of that mechanical intermixing there will be a layer formation in the solid state nature, and it kind of atomic diffusion happens. And in diffusion bonding, of course, there will be a atomic diffusion, but in diffusion bonding, in solid state diffusion, it takes a much longer time to basically have some kind of atomic diffusion. Let's move to the next question. In question, it says again we need to match the followings, which are there are three techniques which are friction stir welding, ultrasonic welding, and diffusion bonding, as I was saying. So as I was saying, in friction stir welding, basically heat generation happens by friction, where applied pressure or there can be kind of extensive stirring of the material. This technique is suitable for wide range of materials, and it can include non-metals or dissimilar metal combination. But in friction stir welding, one of the basic thing is geometry of the components is symmetric in nature. So one of the example what happens in friction stir welding can be aluminum heat sinks to alumina substrate, most commonly used for attaching beams or rods to bulk or sheet components. So I have described this friction stir welding thing earlier also. So you will have some kind of cylindrical tool, and it can be pinless or with pin also. So let us say we have some pin. This pin can have different geometries also. It can be triangular, it can be trapezoidal, it can be hexagonal, and depending on those uh, geometry of the pin, the stirring of the material, the stirring of the materials vary, and depending on that, the material, you can analyze the material flow and how the mixturing of the material at the interface is happening. These things you can always analyze, right? So as I was saying, in friction stir welding you will have a rotating tool, and you'll have a downward plunge of the tool, and then let us say we are doing some kind of lap welding. So this is your penetration depth, right? So if this is x is your penetration depth. And because of this tool rotation and downward plunge, the material of this bottom one, it try to it try to pull up the material towards this uh, material A. Let's say this is material A, this is material B. So material B pulls up towards material B, and because of this mechanical intermixing, solid state diffusion can happen. So for this question, regards this friction stir welding will be matched with extensive stirring of the material, right? And then you have ultrasonic welding. So what happens in ultrasonic welding is the primary mechanism is displacing the interfacial oxides and contaminants using the pressure of the uh, there will be a kind of sonotrode, and the sonotrode will have kind of specific profile, and because of that pressure and vibration of that sonotrode, there will be oxide fragmentation, and the pure metals come into contact, and they form a bond, right? So if you see in ultrasonic welding, there will be kind of geometry. This is kind of, let's say, this is sinusoidal geometry, which can move like this with high frequency, low amplitude, vibration. And here you will have your workpiece. Here you will have your workpiece, and here again you can have some kind of dye pattern, which can again apply some kind of pressure. So your sonotrode trip and dye are able to apply the pressure over the workpiece, and because of this frequency of the sonotrode, there will be kind of at the interface. Here at the interface, there will be kind of shear deformation at the interface, and because of the shear deformation, uh, if you see in ACM or scanning electron microscope, basically you can see the material flow pattern like this. There can be some kind of mechanical interlocking over the interface, right? So in ultrasonic welding here, yeah, this is matching with a high frequency vibration with a low pressure. And as I was saying, the principle of solid state diffusion, which is mainly in the diffusion bonding. In diffusion bonding, the principle of solid state diffusion is the intermix of atoms of two solids. Obviously, in ultrasonic welding and friction stir welding, the solid state diffusion happens through this atomic diffusion only, but there are other mechanisms also to mix the materials. But in diffusion bonding, the primary mechanism is purely dependent on this atomic diffusion of these two solids. That's why it takes so much time to complete this diffusion and to get some proper bond. So in solid state diffusion, the principle is the intermix of atoms uh, of two solids, metallic surfaces in between themselves over time, right? So diffusion is aided by what? Some intermediate heat that can be maybe 50 or 70% of this melting temperature, along with high pressure for a period of time. This period of time can be 1 hour, can be 2 hour, can be 3 hour, depending on material combination. And when the asperities on the two surfaces contact and plastically deform, they interlink and forming interfaces between the two surfaces, right? This technique, as this is purely dependent on atomic diffusion, and there will be no external force applied. Basically, it is a constant pressure, constant temperature process. Constant pressure and constant temperature. So you basically put your workpiece at some furnace where you can apply constant kind of pressure. There will be no external force applied like what happens in friction stir welding. In friction stir welding, obviously the pressure is varying, right? Because of that tool rotation, maybe there will be vibration of the machine. In ultrasonic welding there is also vibration, so for that reason pressures are elevated kind of thing. But in diffusion bonding, it's all constant pressure and constant temperature, and it's all purely on atomic diffusion. So in diffusion bonding it takes very long time to complete the thing. So as I was saying, diffusion is aided at some intermediate heat, maybe 50 or 70% of melting temperature, along with that constant pressure for over a long period of time. And when these asperities on the two surfaces contact and plastically deform, they interlink and form the interface between the two surfaces. This technique results in minimal distortion to components, right? So in diffusion bonding, it's results in minimal distortion to the components. And prior to welding, the surfaces must be machined to as smooth a finish as economically viable, and it should be kept as free from chemical contaminants as possible, right? So otherwise there can be oxide formation, and as it is a constant pressure technique, so maybe it happened that it cannot fragment those oxides. Like in friction stir welding, you are rotating the tool and forcefully you are fragmenting the oxides, and even at ultrasonic welding you are doing it forcefully, right? But in diffusion bonding, there is no external force. It's all constant in nature. So if once you are not you are not eliminating the oxide formation beforehand, it will of course will be detrimental in terms of your bonding. So bonding will be not proper if there is oxide formation, and yeah, so metals will not come into contact. Okay, so let's move to the next question. This is a simple numerical question. It says that in a laser micro welding process, the shape of the pulse is square and the pulse frequency is 500 hertz. We need to calculate the peak power if the pulse energy is given as 10 joule. So what we need to do for this one, we need to calculate the peak power, right? So what do we know in terms of energy and power? We know that power into cycle time. So your pulse is square like this, maybe the laser pulses, and this is your cycle time, which is, I don't know the cycle time, but your pulse frequency is given, right? Pulse frequency is 500 hertz. So from pulse frequency, you of course can estimate the cycle time. Cycle time is 1 by pulse frequency, right? So it will be 1 by 500. How much it will be? Point 002 second. So it's basically 2 milliseconds. So what can we tell about your pulse energy? If we know the power and if we know your cycle time, and if you multiply that power is in terms of joule per second, that into cycle time will give you the pulse energy. As simple as that. So power need to be calculated, that into 0.002, which is your cycle time, that is equal to your pulse energy, which is 10 joule, right? So 10 5,000 watt, which will be equal to 5 kilowatt. There should not be any confusion, I hope, right? Let's move to the next question. Next question it asks, does which one of the following statement is correct about diffusion bonding? So I had already discussed about diffusion bonding. Let's go through this one again. There are four statements. It says the resulting surface must be joined at or below the melting temperature of the red materials. Second statement says the resulting surface must be joined above the melting temperature of the parent materials. Of course, this is not right. Pressure is applied during bonding. Pressure does not play any role during bonding. Of course, pressure plays an important role in diffusion bonding. So, statement one and statement three are correct, right? So, as I was saying, diffusion bonding is a solid state bonding process in which the resulting surfaces are joined below the melting point temperature along with high pressure over a long period of time. Below melting temperature, this can be 50% or 70% of the melting temperature with high pressure over a long period of time. Okay. Let's move to the next question then. In next question, it says, which one of the following statement is correct about conventional friction stir welding? I have intentionally mentioned this conventional friction stir welding because there are some welding techniques which is called micro friction stir welding, which is specifically designed to weld the thin sheets, ultra thin sheets, maybe from 300 micron to 1 mm thick material. If you see this conventional friction stir welding, uh, it mainly welds the sheets of thickness of maybe 2 to 3 mm of thickness. So in terms of conventionality, yes, this is not suitable for thin sheets joining because if you see in micro friction stir welding, let us spend some time to understand what happens in micro friction stir welding. In micro friction stir welding, your sheets are very thin, right? Your sheets are very thin. So these are 1 mm, less than equal to 1 mm. And now let's say in friction stir welding you use maybe 8 to 10 mm of um, shoulder dia, and pin dia can be of 5 mm. I don't know. I'm making some assumptions here. Pin dia is of 5 mm, and then you're penetrating over there, right? So basically, what happens in micro friction stir welding, you have to balance in between the pressure and temperature. So there should have some balance in between pressure and temperature. So if the axial load of the tool is very high, let's say it can generate maybe 8 to 10 kilonewton, and your sheets are very much thin, ultra thin sheets, what will happen? It will basically tear up the material. So if your axial load is very high, it will tear up the sheets. So there should have some kind of compromisation in between. So if you are doing some friction stir welding, there are different kinds of process parameters. It can be axial load, it can be RPM, it can be penetration depth. So there should be proper balance in between this RPM, penetration depth, and this axial load. So basically, what people do is they do some high RPM thing. So your RPM should be as high as possible, depending on your machine capacity. So it can be maybe 4,000 RPM. I have seen papers they have used 10,000 RPM also. So what happens is like the process window is very narrow in microfiction stir welding to get some successful joint. So in one hand you are increasing your RPM so that the heat generation will be high. At the other hand, you are trying to balance the pressure generation, right? If the axial load is very much high, it can tear up the film, tear up the sheet material, right? And another disadvantage in micro friction stir welding is because there is downscaling of this sheet thickness. You have to have downscale the tool dimension, right? There will be downscaling of tool dimension. And as you are downscaling the tool dimension, there will be like the heat affected zone what will be created there. There will be a very rapid heat loss over there, right? The heat generation will not that high, uh, like what happens in conventional friction stir welding. So this is one of the, you can say this is one of the disadvantage, and you should take care uh, during process parameter selection in micro friction stir welding. And the second statement says it depends upon high frequency vibration of tool. There is this is not the mechanism as such. Yes, there can be kind of machine vibration, but the tool is not the tool will not be vibrated during rotation and plunging action, right? So this is also a false statement. And it forms a keyhole after penetration. Yes, this will form a keyhole after penetration. If you see some kind of some welding there, if you have seen and you see the top view, you will see there kind of keyhole forms over there, because you are penetrating the tool pin over there, and then you are retracting the tool after the processing. So there will be the impression of that pin over there. uh, this defect can be hazardous in terms of this thermal conductivity, in terms of electrical conductivity. So yes, there also should be some kind of care should be taken in terms of removing this keyhole defect. Sorry. And in the last statement, it says pressure does not play any role during bonding. This is also a wrong statement. So the correct statement is it forms a keyhole after penetration. This is the correct statement. Statement 3 is let's move to the question number 6. In question 6, it's again asked about different kinds of welding techniques and to match the following. So, initially, to start with, the first one is ultra short pulse laser welding. In ultra short laser pulse welding, the pulse duration is in the order of femtosecond to picoseconds, right? So, this one is correct. And the duration of laser pulse are shorter than the time required for energy to be transferred to the surrounding area. But in long pulse laser, the pulse duration is in nanoseconds and maybe greater than that. So in long pulse laser, the pulse duration is in nanosecond or maybe greater than that. Then comes to resistance micro welding. In resistance micro welding, it is different from large scale resistance welding. In micro welding technique, the electrode pressure is much lower, and this lower electrode pressure results in higher contact resistance. So in resistance micro welding, electrode pressure is low, which results in higher contact resistance. And if the contact resistance is higher, what will happen? It reduces the welding current. Welding current reduces, and that results maybe some kind of it can promote electrode sticking. These are some kind of characteristics in resistance micro welding. And in micro welding, the maximum nugget diameter is about, you can say, 30% of the electrode diameter. So nugget dia, 30% of electrode dia. Okay. And then there is laser droplet welding. Uh, I need to use. Okay. Let us try to use this portion. So, what happens in laser droplet welding? Here, the welding is realized by a laser generated liquid metal droplet, which is deposited onto the parts to be joined, right? So, there will be a liquid metal droplet creation because of that laser, and it will deposit over the parts. And the raw material is a metal wire. In conventional laser welding, a gap between the parts uh, this is a common, you can say, research gap in conventional laser welding. It cannot feel the gap between the parts, and it worsens the quality of the laser welded joint substantially. But contrarily, a droplet offers a sufficient material to bridge those gaps. Even different gap sizes can be bridged by a suitable selection of the droplet size. What can be a further advantage? A further advantage is controllable heat transfer. So in droplet welding, there will be a controllable heat transfer only given by the heat content of a single drop that is sufficient to maybe produce a high temperature weld. And this droplet heating provides the opportunity to weld small devices, very small, thin coatings, and even heat sensitive components without negative influence on their mechanical and electrical functions. It is also possible to, what should I say, to interconnect different materials by addition of material supplied in the form of drops, right? So if you try to draw the I should not say the graphs, but try to figure out in terms of schematic what happens in droplet welding. There will be a five phases. So you have already gone through this. Let's recapitulate the thing again. So there will be a five phases. This is power versus time. Here, droplet creation by melting occurs, and then there will be some kind of droplet detachment, there can be droplet flight, and there can be droplet landing, and then finally you will end up with droplet solidification. So initially you create the droplet, then you move to the position where you want to deposit the droplet, and then finally the droplet is retouched here. So what are the five phases here? One is droplet creation. Second is droplet detachment. Third is droplet flight. Fourth, droplet landing. And the final one is droplet solidification. Right. So in resistance micro welding, yes, heat is generated by electrical resistance. Laser droplet welding, it overcomes the gap bridging, and there is something called laser transmission welding. So if you see in laser transmission welding, a high beam of so in laser transmission welding, a high beam quality laser like maybe fiber laser is used, where easy degradation of thermoplastic materials is possible. The basic principle is like this. The basic principle of this joining method is uh, initially there will be passing or transmitting a laser radiation through one piece of plastic to create a weld. And unlike standard welding, where the energy is applied at the surface of the materials, transmission welding aims to apply the energy in between the two plastic pieces at their interface. So, if you try to figure out what can be a schematic, so there will be two plastic pieces. This plastic will be transparent in nature, right? So the upper layer needs to be transparent to laser wavelengths, maybe in the infrared or near infrared spectrum. And once the laser beam passes through this upper layer, it still needs to be converted into thermal energy, right? So this happens at the interface of the two joining parts, and the lower part needs to have the ability to absorb that energy to create the heat. So this part should not transmit again. This should absorb the energy so that it can create the heat over there and it can form the bond. So the most common and best absorbing additives is people mostly use carbon black. Let me choose different color. So people use carbon black doped at a rate of about 0.5%. Okay. So in laser transmission welding, it's mainly used for welding of thermoplastics. In question 7, it asks that suppose a user wants to convert the scanning electron microscope into an electron beam microwelding setup. Which of the following must be removed for a microwelding setup? Uh, if you see in scanning electron microscope, it works on the principle of targeting a focused beam of electrons moving with high kinetic energy on a specimen. And when these electrons scan the surface of the specimen, electrons are scattered, right? And those secondary electrons that are slowed down on the impact of hitting the surface are collected by a detector, and these secondary electrons create the magnified image of the specimen, and it can then thereby illustrate the morphology, topology of the specimen. So in ACM, multiple apertures are used for screening off-axis electrons. Basically, they stop the electrons, those are off-axis and off energy, from progressing down the column of the column of those electrons. They generally reduce the effective beam power. And two condenser lenses also used in ACM, which are used for the reduction of excess electrons. So, what are the functions of condenser lens? It focuses and controls the electron beam, ensuring that electron beam end up precisely where they need to go, right? And if you want to convert the ACM thing in electron beam microwelding setup, what we need to do? We need to simply remove the apertures and one condenser lens, and that's how one can develop the setup for welding. So we need to remove the apertures and so let us try to draw some schematic. I'm not sure I can able to do that or not, but let us try to do that to understand what happens in ACM principle. Let me take this portion of this presentation. So in ACM, basically, you will have some kind of electron source over here, and then sorry, electron. You'll have one condenser lens, then again one condenser lens. Sorry, and then this will be your aperture, which will screen the excess electrons. This is your condenser lens, where it is focusing the beam and in much controllable way. And there can be kind of what should I say, scanning coil, and finally there will be objective lens. And then you're focusing it finally. Here you have your sample. Then your electron beam is colliding with sample and it is getting straightened through. And then here you have your system. There can be kind of detector over here which can detect this secondary electrons, and there can be an amplifier which will amplify the image, and you can see the ACM image of your specimen. Okay. Okay. So yeah, this is the last question of today's session. Here in this question it asks, in resistance microwelding, the resistance microwelding is performed on two sheets of 0.2 mm thickness with 3.2 mm diameter electrode using a 1000 ampere current for a time duration of 100 milliseconds. Suppose the overall contact resistance between the joint sheet is 0.00015 ohm. We need to calculate the heat generated to form the weld. So let us try to figure out what are given and what need to be calculated. So here the current value is given. I is equal to 1000 ampere. Resistance value is given 0.00015 ohm. T value is given, which is 100 millisecond. Oh, this is very much simple in terms of uh, understanding the thing. So you need to calculate simply the heat generated to form the weld. So what will be the heat generated? Is simply I square RT, right? So your I value is given as 1000, that into 0.00015, that into 100 into 10 to the minus 3. So this is in second, right? So this is 10 cube, 10 cube square, 10 to the 6 into 10 to the minus 3 into 100 to 0.00015, that into 100 to 10 cube to 15 into 10 to the power minus how much? 5. Which is coming as 15 joule. So the heat generated to form the weld is 15 joule. Okay, that's it for today. If you have any confusion, you can always contact me. Let us finish today's session here then. We'll meet next week again.